Hello everyone. Kinetics of complex reactions, part 4. I have already made videos on all the four kinds of, on all the three kinds, that is opposing reactions, parallel reactions and consecutive reactions. I have also made a small video on general characteristics of chain reactions. Now in this video today, we are going to study about steady state treatment for the study of kinetics of chain reactions. So let us get into the topic quickly. According to steady state treatment, the concentration of free radical, we have already seen about this in the general characteristics of chain reactions in my previous video. Kindly watch it to get a better connectivity. Now I'm getting along with the topic quickly. That is, according to this steady state treatment, what is said is that the concentration of free radical chain carrier is constant. Any instant. So, R will be considered as a constant. That is, R is nothing but free radical. Or you can say intermediate chain carrier. So, dr by dt, concentration of this free radical by dt will be equal to 0. So now let us apply steady state treatment to the general chain reaction. What we get is M, which is a reactant, at K1 will go to R. Now here in the first step, as I said in my previous video, first step, it is chain initiation. That is, initiation takes place. Something will initiate the reaction. Initiation. The second step, M plus R continues. That is, you can say branching. Branching, or we can say propagation takes place. Continuous reaction keeps happening. Now M plus R further, that is, after branching, after propagation, finally it will form the product. Now this product that is formed, or the next step you can say R, the free radical that keeps forming at K4, destruction at surface. And the last one, if it is in a gas phase, so destruction gas phase. Now, the first of the above reactions use this one. Is the initiation, that is the first of the above all these reactions, is the initiation reaction in which free radicals are produced. These are the free radicals that are being produced. In the second reaction, R undergoes an elementary process with the production of more than one radical. In the third reaction, products are formed along with a radical. Now reactions 4 and 5. These two are supposed to be chain ending. Processes. Okay. Applying the steady state treatment to the radical R, dr by dt, what we get is K1m plus K2 minus 1 Rm minus K3 Rm minus K4R minus K5R, which will be equal to 0. Or we can say R is equal to write down the direct step K1m by K3m plus K4 plus K5 minus K2 alpha minus 1 m. So, the overall rate of the reaction is given by step 3. This step will give us the overall rate of reaction. That is V is equal to K3 Rm. We know the value of R. So on substituting the value of R, that is However, on substituting this value over here, K3, K3, K1M, here I forgot to put, so I'm putting the bracket here. It is concentration. Is M here, M here, M here. So it is M square and down everything as it is. K3 concentration of M plus K4 plus K5 minus K2 alpha minus 1 concentration of. Now chain length of a chain reaction is defined as the overall reaction divided by the rate of initiation reaction. So chain length will be is equal to V divided by K1 concentration of M. Which will be equal to K3 K1 M square divided by K3M plus K4 plus K5 minus K2 alpha minus 1 concentration of M, and what is left over, what this is left over, that is K1 concentration of M. So this whole thing multiplied by K1M. Since this is common, K1M gets cancelled, and what answer we get is let's use another pen to cancel it out. K1 gets cancelled, M gets cancelled. So what we are left out with is K3 M divided by K3 concentration of M plus K4 plus K5 minus K2 alpha minus 1 M. So normally in the branching reaction, alpha is greater than unity. So that the last term in the denomination of this expression alpha will be greater than unity. So that the expression for rate will become positive. Therefore, it is possible for the denomination it can be 0. Under these circumstances, the rate in principle becomes infinite. But in reality, the rate becomes very large. So when K2 alpha minus 1 concentration of M. Now this term, when it becomes equal to K3M plus K4, K5, these two terms, when they become equal, the rate becomes very, very large. And this condition of explosion limit is reached. At such a condition, it can explode. So this was it for a steady state treatment for the study of kinetics of chain reactions. Now with an example, I'll continue in my next video. Do not forget to watch it. I'll be uploading all the kinetics of complex reaction. Do keep watching. Watch the playlist for a better connectivity. Thanks for watching.